In this video, we're going to continue to look at the topic of atomic structure in the A-level syllabus. As mentioned in the very first video, there are two new parts to this chapter in the A-level syllabus. The first is to write the electronic configuration of atoms and ions in terms of subshells and orbitals. And then the next part is to look at the ionization energy trend to be able to explain and then to be able to use the trend to deduce the identity of atoms and elements. So in this video, we are going to focus on the concept of ionization energies and how they relate to the electronic configuration that we have learned to write in the A-level syllabus. Now, for a start, we must first define what is ionization energy, and the real definition would come in when we are looking at the chapter of chemical energetics. So for now, it is useful to just remember that ionization energy is the minimum energy required to remove the outermost electron. Okay, as mentioned, this is not the most accurate definition of ionization energy, but it's useful for this chapter to just remember that it's the minimum energy required to remove the outermost electron. Now we look at the plot of first ionization energy versus proton number. Now what does first ionization energy mean? It means the minimum energy required to remove the first outermost electron. Okay, so second ionization energy would be the second outermost electron. So after removing the first electron, the energy required to remove the next outermost electron is known as the second ionization energy. So now if we look at the plot of first ionization energy versus proton number, or versus the elements as we go across the period, there are certain trends that we can actually observe, and we can learn to explain now that we have learned how to write the electronic configuration for the different elements. The first trend that we can observe is this, that when we move across a period, the first ionization energy of the successive elements increases. Okay, why is that so? We have briefly learned this in O-levels, right? We have learned that ionization energy involves removing the outermost electron. All right, so what holds the outermost electron in the atom is the electrostatic attraction between the protons in the nucleus and the electron. Okay, so what happens when we move across the period is this, that the number of protons increases. Okay, so as the number of protons increases, the magnitude of the positive charge in the proton will increase. Okay, in higher levels we call that the nuclear charge. Okay, so as we move across the period, number of protons increases, nuclear charge increases. But that's only half the story that we learn in O-levels, right? Why is that so? Because actually, when we move across the period, we have more protons, but we also have more electrons. And what happens when you have more electrons is this, that electrons, they actually repel each other. Okay, like charges repel. Okay, so this repulsion between electrons which have the same charge is known as your shielding effect. Okay, and an increase in repulsion and an increase in shielding effect would mean that the electron can be removed more easily. Okay, so let's think of this again. As we move across the period, the nuclear charge increases because we have more protons. The shielding effect also increases because we have more electrons. So when you have two opposing effects, how do we know what is the net outcome? Which one would outweigh the other? Right? In science, whenever we have two opposing effects, the only way to find out is through experiments. all right, by measuring the actual ionization energy, and we find that it actually increases across the period. So what does that mean? It means that the increase in nuclear charge outweighs the increase in shielding effect. And how do we explain for that? It's because when we go across the period, the electrons are added to the same quantum shell. Okay, so imagine if you are in a concert and people start coming and occupying the seats along your aisle. All right, will they block you from seeing the concert? The answer is no. All right, so as more and more people come in and sit alongside you, it doesn't really affect your view of the stage. The increase in shielding effect is insignificant. So what's the result of that? That the increase in nuclear charge would outweigh the increase in shielding effect. So therefore, across the period, first ionization energy increases. Okay, this is a common question in A levels, so you will need to be able to answer it using these 3 points. Okay, number of protons increases, nuclear charge increases. Electrons are added to the same quantum shell, so increase in shielding effect is insignificant. And the third point that must be included in your answer is that the increase in nuclear charge would outweigh the increase in in shielding effect. Okay, so the net attraction is known as your effective nuclear charge. So your effective nuclear charge increases across the period. Now, so what we have seen is that the first ionization energy, it generally increases across the period. So we are looking at period 2 over here. Alright, but if you look at the graph at the very beginning and the graph that I've drawn here, you would find that there seems to be 2 exceptions. One of them would be boron, the other one would be oxygen. Okay, and if you analyze that for the period 3, elements in period 3, you would find the same exception with aluminium, alright, the element that's below boron, as well as sulfur, the element that's below oxygen. So on top of being able to explain for the general trends, we must be able to explain for these 2 exceptions as well. In order to explain for the exceptions, we need to write the electronic configuration. Alright, that's where the concept of electronic configuration comes in. We need to be able to write the electronic configuration for boron, okay, as well as oxygen. So let us do it now. The electronic configuration for boron is actually 1s2, okay, 2s2, and then 2p1. Okay, boron has 5 electrons. So if we take a look at the outermost electron to be removed, okay, you will find that it comes from an outer subshell. Okay, when an electron resides in an outer subshell, it is actually further away from the nucleus. Alright, hence the electron is less strongly attracted to the nucleus, which means this particular electron can be removed more easily. Alright, so that explains why boron has a lower first ionization energy than beryllium. Okay, if we look at beryllium, I'm just going to write down, this is for boron. Beryllium has this particular electronic configuration. So the first electron to be removed is actually from an inner 2s subshell. So in this case, it requires more energy. Now, similarly, to explain the exception for oxygen, we must first write down the electronic configuration of oxygen. So oxygen has 8 electrons. It would have this particular electronic configuration 2p4. And in particular, to explain for the exception for oxygen and sulfur, you need to write the electronic configuration in this particular way. You need to expand the 2p subshell to show the orbitals that are involved. Meaning, for this particular case, you need to write your electronic configuration in this particular way, 2px2, 2py1, and 2pz1. Okay, why is it important to write your electronic configuration this way? Is because it shows this in your 2p subshell. Okay, the electrons are arranged in this particular manner. And now let's take a look at the outermost electron to be removed. It is actually this electron. And why is this electron more easily removed as reflected by the lower ionization energy? Is that this electron is in a paired orbital, is in a paired p orbital. Okay, imagine if you are sitting happily in a bus seat, someone comes and sit beside you, you feel very uncomfortable, you want to push the other person away. So that is why that electron can be removed more easily due to the inter-electron repulsion. Right? So as mentioned, other than being able to explain for the general increase in ionization energy across the period, you need to be able to explain for these two exceptions. For boron and aluminium, the first electron to be removed comes from an outer subshell, outer p subshell, further away from nucleus, less strongly attracted. For oxygen and sulfur, the electron to be removed comes from a paired p orbital. So there's inter-electron repulsion, which causes the electron to be removed more easily. Now, if we analyze the trend of ionization energies down a group, you would realize that the first ionization energy decreases down a group, meaning sodium, which is lower than lithium in the group, would have a smaller first ionization energy. Now, how do we explain for that? This is where your O-level knowledge would fail. Right? Why? Because as we go down the group, sodium should have more protons than lithium, isn't it? So sodium there should be a stronger attraction on your outermost electron. So sodium by right should have a higher first ionization energy. Okay, so that the error comes in because we only consider your nuclear charge. By now you should know what is a nuclear charge, but we ignore the shielding effect. So what happens is this: when we go down a group, correct, as we have learned in O-levels, number of protons increases, your nuclear charge would increase. But now, as we go down a group, the electrons are added to an outer quantum shell. Okay, now this is equivalent to you coming into a concert hall, alright, occupying the back rows where you have many people in front of you. So what happens? The people in front of you is going to block your view of the concert. Okay, so when electrons are added to an outer quantum shell, the shielding effect, the repulsion increases significantly. Okay, but once again, how do we know whether which effect would outweigh the other? It can only be obtained from experiments. It can only be obtained empirically. Empirically, we found that the increase in shielding effect, in this case, when we go down a group, outweighs the increase in nuclear charge. So what happens to the net attraction? The net attraction decreases as we go down a group. So same thing, how do we explain the trend going down the group? We need to have 3 points. Number one, number of protons increases, nuclear charge increases, but electrons are added to an outer quantum shell. So shielding effect increases significantly. Increase in shielding effect outweighs the increase in nuclear charge. Therefore, effective nuclear charge decreases. Now, a common type of question that you will get in the A-levels pertaining to ionization energies is for you to deduce the group number of an unknown atom based on your ionization energy data. Okay, there are two types that you will get. The data can be for successive elements. Alright, so this is what we have seen earlier. So for example, in this case, the first ionization energy is given for successive elements. They ask you for the group number of this unknown X. Now, as a student, how I would solve this kind of question is that I would draw out the trend, the overall trend over 2 periods. So for example, I will draw something like this. Okay, and then I will put in the group numbers. For example, this is group 1, 2, 13, 14, 15, 16, 17, 18, and then this is group 1 again. Alright, and then from the graph given in the question, I'll try to spot which segment of the graph are we looking at. For example, in this particular question, we are looking at actually from 14, alright, all the way to 1. So we are looking at this particular segment of the graph. Okay, and then I'll go on to look at where is X on the graph. X is actually here. X. Alright, so X belongs to group 17. Okay, so once again, if you are given a graph of first ionization energy versus proton number, or for successive elements, how do you identify the group? Is to quickly replicate the first ionization energy graph across 2 periods, and then quickly look at which segment is represented in the question, and with that you should be able to identify the group number of the unknown atom. Now for some harder questions, what they would do is that instead of giving first IE, they will change it to second IE, and now the trick remains the same. I would still replicate the ionization graph for 2 periods, but the trick now is to shift the group numbers 1 to the left. Alright, so meaning this would correspond to group 2, group 3, group 13, group 14, 15, 16, 17, 18. This will be group 1 and this will be group 2. Okay, so if we are looking at second IE, now X would be here. So X would correspond to group 18, a noble gas. Okay, so if the question gives second IE, you can still use the same method but move the group numbers 1 to the left. Okay, that means for the very first element, it's not in group 1 but it's in group 2. And then what happens if it's third IE, then you move it 1 more, the group numbers 1 more to the left from the trend that you have drawn. Now the second type of question that you will get is the ionization energies for successive IE. Alright, not for successive elements, but for the same element, for one element, but successive IEs. Okay, in this case, the trick is to look for the big jump. Okay, why? Because the big jump would tell you that the electron is removed from an inner quantum shell. Okay, so for example, if we look at atom X, where is the big jump? The big jump is very obvious. It occurs between the 5th and the 6th IE. So what does that mean? It means that the 6th electron, okay, comes from an inner quantum shell. I repeat again, the 6th electron comes from an inner quantum shell. So how many valence electrons are there in atom X? There are 5 valence electrons. That would mean that X is in group 15. So if we look at atom Y now, atom Y, where is the big jump? The big jump occurs here between 6 and 7. Okay, so what does this mean? It means that for atom Y, the 7th electron comes from an inner quantum shell. So how many valence electrons are there in atom Y? There will be 6 valence electrons, meaning it is in group 16. Okay, and the last one over here, the biggest jump occurs between the 7th and the 8th electron. So what does this mean is that for atom Z, the 8th electron is from an inner quantum shell. Okay, So how many valence electrons are there in atom Z? There will be 17 valence electrons. So it is in, sorry, there will be 7 valence electrons, meaning atom Z is in group 17. Okay, so the trick when analyzing data for successive IEs for a particular atom or element is to look for the big jump, which will tell you that the electron comes from an inner quantum shell. Now, sometimes you'll be asked to explain the trend in successive IE for a particular atom or element. Meaning, if we look at the question before, we would see that the second IE is larger than the first IE, the third IE is larger than the second IE. So successive IEs increases. And how do we explain for that? Is to recognize that with each successive IE, alright, the number of remaining electrons decreases. Okay, however, the nuclear charge remains the same. So the remaining electrons would experience a greater net attraction. Okay, so therefore, as we look at the successive IEs or successive electrons to be removed, it will require a greater amount of energy. As mentioned, when you see a big jump in ionization energy, that is signal to you that the electron is removed from an inner quantum shell. Sometimes if you analyze to greater detail, you will see small jumps in IE. Alright, small jumps, they actually correspond to a removal of electron from an inner subshell. Okay, same thing if we compare the S and the P subshell for the same quantum shell. The S subshell is slightly lower in energy than the P subshell. Okay, so when we remove an electron from an S subshell, a 2S subshell, as compared to one from a 2P subshell, the one from a 2S subshell would require a larger amount of energy. Alright, so you see a small jump in the IE trend.